So last time we had the midterm on Thursday, not completely done grading the midterm. I'm going to try to get the marks posted for that as soon as I can, as well as the grading for the assignments. So I hope within, at least by the start to beginning of the midterm week, you should probably get all your marks posted on PHYS, so everyone will know where they're at. And I'm going to post the solutions to the midterms. You'll get your midterms back as well. But I'm not going to go through the midterm problems in class. What I'm going to do is post solutions, and then you can look at those. Based on the bit of marking that I do have done, it seems like the midterm was done pretty well in general, so I think the marks are going to be pretty good. Okay, so before the midterm, we're working towards moving from kinematics to dynamics. And so we started off the course thinking about how parcels basically move in a velocity field. So you're given some velocity field, we're calculating trajectories using the kinematic equation, that sort of thing. But then what we're working on now is trying to understand where do those velocity fields come from? How would we actually predict a velocity field? And what is the physics of how those things change? And so that's really into what we call dynamics. So it involves things like forces, acceleration, that sort of stuff, as opposed to just moving with a given velocity. And so we're working towards developing the dynamical equations of fluid mechanics. And last time we got to this equation, which is really the first predictive equation that we've written down for the flow itself, which is the Euler momentum equation, which is at the bottom here. So let's just go through what we talked about last time. So we started off about the molecular origin of pressure. So we discussed how pressure is really the most sort of quintessential fluid force. It's the force that really only shows up in fluid problems, whether that's flow in a pipe or flow in a star, in astrophysics or in the ocean or the atmosphere. All of those environments have pressure forces. And then there are also other forces that we're going to consider as well, like gravity and friction and things like that. But those are more generic. They show up in all sorts of physical systems. But pressure is really a fluid property. And we talked about how that pressure, which we think of as a field, pressure is just a function of space and time. But the origin of it is really molecular interactions. The fact that fluids are, any fluid, whether it's a gas or a liquid or whatever, is made up of molecules. And those molecules collide with things. They collide with each other and they collide with the walls. And those collisions give rise to the pressure force. And that pressure, because it has a thermodynamic origin, because it's based on statistics of many, many molecular collisions, it's related to the other thermodynamic type variables of the fluid. And the classic example is the ideal gas law here, which we often call IGL, or ideal gas law. And the ideal gas law is a very, very simple equation that describes a certain type of fluid, the ideal gas, and it shows that the pressure, the density, and the temperature are locked together very rigidly in this three-part formula where there's a constant coefficient in there that we call the gas constant. Depends on which specific gas you're looking at. But this ideal gas law is very illustrative because it shows how we generally expect pressure to change when other thermodynamic variables change. And so, for example, when temperature increases, if you were to double temperature, for example, in Kelvin units, then this right-hand side would double, and that would tell us that the pressure doubles. And that we talked about why that is, and it's associated with the fact that when you have a higher temperature, that means that the molecules that are inside your fluid are moving faster, and so when they hit the wall, they hit harder, and that's a higher pressure force. And similarly, if you double the density, that also doubles the pressure. And that also makes sense from a molecular point of view, because if you have twice as many particles in a given space, then you'll have twice as many collisions. And so you have more instances of momentum transfer, and the net force is higher. So for a fluid like the ocean, a liquid, and a complex liquid, like has water in it, has salt in it, has dissolved carbon dioxide in it, it turns out the internal physics of water is much more complicated than the ideal gas. And so you can't write a very simple formula that just says pressure equals to like some function that's explicit of density, temperature, and salinity. But it is still true that the pressure of the ocean and seawater depends on the density, temperature, and salinity, and there is some kind of rigid functional relationship that connects these. Just like, you can think of it just like the ideal gas law, but it's so complicated that we need some kind of computer program to compute it. We can't just do it using a simple formula. And we call this kind of formula in general the equation of state, and we abbreviate that EOS. And so the equations of state are just formulas or relationships that link together the thermodynamic variables of the fluid. So In the case of ideal gas, all you have is pressure, density, and temperature. And in the case of the seawater, you have density, temperature, and then also salinity. Okay. So this is just sort of a general discussion. And later in the course, we'll actually talk about equations of state for the ocean, but more concretely when we talk about ocean acoustics and sound waves. We then talked about the pressure gradient force. So when the pressure is this squeezing force, so any object that could put into the ocean gets squeezed, and generally, and if the nature of the squeezing is uniform, so that if the pressure is the same everywhere, and you're squeezing the same on all the different sides, then there's no net force on the object. So it's not going to, the center of mass of that object is not going to move. But if the pressure varies, so you have, say, high pressure on one side and low pressure on the other, then you'll tend to have a force from high to low pressure that can actually push objects. And we derived this formula for the pressure gradient force. It says that the force, the net force due to pressure on an object is equal to the negative pressure gradient. So we talked about the gradient of pressure multiplied by the volume of the parcel. So I'm going to do a little bit of dimensional analysis on this before we get started, but the key thing is that when we have pressure, it's the gradient of pressure that creates the force, and it comes with a minus sign. And the minus sign is really, really important because the gradient, when we introduced the notion of the gradient, we said that the gradient points in the direction of steepest increase of the function. So that means minus the gradient is exactly the opposite of that vector, so it points in the direction of fastest decrease. And that makes sense for the pressure gradient because the pressure pushes from high pressure to low pressure. So we want to go down the pressure gradient, and that's the way the force works. And so that's why there's this very critical negative sign in the formula. And then based on this pressure force, we can now start using Newton's law. So eventually we're going to incorporate multiple different forces into our dynamical description of fluids. But just to start off with, we can think about just the pressure and ignore things like friction, ignore gravity. Those will become important when we talk about ocean surface waves. At least gravity will. So at the end, we talked about this equation called the Euler momentum equation. And where that comes from is just Newton's second law. So F equals ma is a formula from first year physics. Your force equals your mass times acceleration. And then for a fluid parcel, if we have a parcel of fluid, then the mass of this parcel is equal to, if it has length, say, delta x, delta y, and delta z in the vertical, then your mass is equal to the density times delta x, delta y, delta z, which we sometimes write as rho delta v, where delta v just equals the product of those three linear dimensions. So when we plug in F equals ma, we have our mass is rho times delta v. We know our acceleration from the very first part of the course is du dt, the material derivative of velocity equals the acceleration. And then the force now is just the pressure force. So if we put in this pressure force for our F, so F equals Fp equals minus the small volume times the pressure gradient, we get here, we would get, so F equals ma, so F would be minus delta V, that's the small volume, times our pressure gradient. Our mass is our small volume times our density. Our acceleration is du dt. And the nice thing that happens is the small volume appears on both sides of the equation. So we cancel that out, and what we're left with here is capital du dt, if we divide through by density, is equal to minus 1 over rho times the pressure gradient. And so acceleration, we've kind of written it as acceleration equals 1 over mass times force. And it's the conventional way this is written in fluid mechanics. And this is a predictive equation. We're going to solve this equation today in a simple example. Because this has a time derivative, it's a material derivative, but there's a time derivative on u, that means it's a differential equation, a partial differential equation, for the velocity field itself. So if we know what the other factors are, if we know the pressure, we know the density, for example, we can actually solve this equation to predict what the velocity will be in the future. And so this is the kind of thing we want to do for example, numerical weather forecasting, or whatever. We want to predict what the winds are like in the future, and this is the kind of equation that allows us to do that. And then at the very end, we started counting variables, and we wanted to ask, is this equation, can we actually just go ahead and solve this now, or do we need more information in other equations? Are we sort of ready to go just with this one, or do we need more information? And to assess that, what you normally do is you count how many unknowns you have and how many equations you have. It's just like linear algebra. You have 5 unknowns, you need 5 equations. So in terms of variables, there are really 5 variables in this equation. So it's important to remember that this is a vector equation. This equation, because we have vector symbols here, this is really one equation for the x, y, and z components. So this equation is really 3 equations. So we have an equation for u, v, and w. So u, v, and w are three unknowns. Density is an unknown, as is pressure. So written here, you have 5 variables, u, v, w, p, rho. That's 5 variables. We have 3 equations. This vector equation gives you 3 component equations for x, y, and z. So we're really not done. We can't actually solve this equation on its own because we don't have enough information to constrain the density and to constrain the pressure. And so we'll talk today about some ways to augment the Euler momentum equation with other pieces of information that will allow us to actually solve it. Okay, but before proceeding, I just wanted to do a little bit of dimensional analysis here on this pressure, just making sure we can understand this pressure gradient force. Does it have the right units? So I'm just going to do a short little section here on dimensional analysis of pressure force. So what are the dimensions of grad P, the pressure gradient? So the dimensions of grad P are the same as the dimensions of dp dx, because dp dx is one of the components of grad P. And so whenever you have a derivative, the dimensions of a derivative are equal to the dimensions of whatever's on top divided by the dimensions of length. You can sort of think of this as being the dimensions of x. You have a p on top in your derivative and an x on bottom. So this seems kind of sloppy, but it's actually rigorous. The numerator is the dimensions of p, and the denominator are the dimensions of x. So we know that pressure is equal to force over area. So the numerator is the dimensions of force over area, and our bottom is the dimensions of length. So this is equal to the dimensions of force divided by length times the dimensions of area, which is then the dimensions of force divided by length cubed, because the dimensions of area is length squared. So this is working out nicely. It says that, and this is just sort of a good thing to have in the back of your mind, that a pressure gradient has dimensions of force per length cubed, or force per volume. So this is force per volume. Now, dimensions of force they're not a fundamental unit. We could break that down further into mass, length, and time. But just to illustrate that this pressure gradient force really has the proper units of force, now the dimensions of Fp are equal to the dimensions of delta V times our pressure gradient, which is the units of our small volume times the dimensions of pressure gradient, which are length cubed. The dimensions of volume are length cubed. Our dimensions of pressure gradient we just worked out are the dimensions of force per length cubed, and so we just get dimensions of force, which is what we wanted. So just in case some of the gradients and delta V's and things seem strange, they all work out dimensionally. So if you just have a pure pressure gradient, that's a force per unit volume, and then we multiply that by our little delta V, we get units of a force. So when we write down this F equals ma equation, we're sort of really thinking about it on a per volume basis, because this thing here is really sort of a force per volume, the pressure gradient. Okay. Does anyone have any questions about any of the review or anything? Okay. So now we're going to try to take advantage of some of the stuff we've developed and try to solve this Euler equation and see if we can understand some of its properties, what types of things does it predict. So the first section, I'm just going to call a simple way to close the Euler equation. And when I say close, all I mean is add other information so that the system is solvable, so that you have enough information you can start solving. So, so we need two more constraints or equations to close the system. A very simple way is to make the assumptions. I'll say for example purposes. So in a general flow, you won't be able to make these assumptions, but they'll illustrate how we can solve the equation. So we're going to assume that density is constant. So that means that rho, which is normally a function of x and t, just equals rho naught equals constant. And in many circumstances, actually, this approximation is pretty reasonable, because in the ocean, density only varies by like a few percent. Sometimes those density variations are very important, but in many circumstances, it's acceptable to get a decent amount of accuracy to assume that the density is constant. We also need something about the pressure, so we're just going to assume the pressure is given. And this will basically never happen in a real problem. You won't know what the pressure is in advance unless you maybe measure it. Maybe you're combining theoretical techniques with observations. And so in this case, we're going to assume that P, which is normally a function of x and t, is just going to be equal to P naught plus a constant A times dot t times x. So what that means is that our pressure is going to look something like this. So we're just assuming a very, very simple form of pressure. You can imagine you have some kind of pipe, and then there's an applied delta P. There's an applied pressure gradient across this pipe, and it creates this pressure field that we're just assuming. And so this is really just for the example purposes to see how could we solve the equation if we have enough constraints, with density being constant and pressure being given, that now we should in principle be able to solve Euler's equation to predict the velocity field. So we can now predict the velocity given an initial condition. I'm going to assume that u of x and t equals 0 is 0. So we start at rest. Okay. So let's leave that there for a minute. So if our pressure looks like this, so the pressure is increasing as you go to larger values of x, as you move to the right, the pressure is getting higher and higher, and it's getting lower and lower on this side. So we basically have high pressure on this side and low pressure on that side. And we're starting the flow at rest. So, does anyone have any intuitive idea or a guess for what's going to happen to the flow? Is it going to start moving? Is it going to stay still? Which direction is it going to start moving? What are the sort of forces? Does anyone have a comment on what they sort of expect? We're going to solve for the velocity now in a minute. But does anyone have any expectation for what's going to happen? Is it going to stay at rest? Is it going to move? Which way? You can think about the pipe example concretely. Imagine you have a pipe, it's full of water, the water's just sitting in the pipe, not doing anything, stationary. Now you apply a pressure difference. So this side of the pipe is highly pressurized, and this side of the pipe is not as pressurized. You have high pressure on this side, H, low pressure on this side, L. So what's going to happen to the water in the pipe?
Move from the H to L.
Yeah, from right to left. Right? Yeah, so there's going to be some kind of pressure force pointing this way. So generally, we expect the velocity to start. It's going to start moving, and it's going to go that way. So it should be. So our velocity in the end should be negative. If that's positive, this is negative. So we should be going that way. Okay. So that's again. So it's a good idea when you're doing a physics problem to have some idea in your mind before you start like crunching through algebra and stuff what the end answer should look like in general terms. You might not be able to come up with a formula, but in general qualitative terms, what it's going to do. And so for this simple example, high pressure on that side, low pressure on that side, the high pressure is going to push the flow this way. So we should have some kind of U less than 0 as our result. Okay. So now let's show that that's true mathematically. Okay, so let's solve the Euler equation in this scenario. So, our equation is the u dt equals minus 1 over rho, that's the pressure gradient. And we know rho equals rho naught is constant. We know the pressure is P naught plus AX. And so that means that our pressure gradient is equal to d by dx. Sorry, it's dp dx, dp dy, dp dz. This only depends on x. So our answer is going to be dp dx is just a here. So we have a 0, 0. So that's equal to a times x hat. And because our pressure force is only in the x direction, we don't have anything happening in y or z, we can assume that we can rigorously assume that that v and w equals 0, and that u equals u possibly of x and possibly of time. So we're not going to have any flow in the vertical or into the out of the page directions. In the east-west direction, we have some velocity field. Maybe it depends on x, maybe it depends on time. We don't quite know yet. So we have here our material derivative comes down. We have partial by partial t plus u partial by partial x plus v partial by partial y plus w partial by partial z acting on the vector UVW equals minus 1 over rho hat times the vector A 0, 0. That's our pressure gradient. And we've made this assumption that V and W are both 0, so we can cross those out, cross this out here. And so we just get a very much simplified version of our equation that is just partial by partial t plus u partial by partial x of u is equal to minus a over rho naught. So that's the x component of the three-dimensional vector Euler equation. But in this case, because we're assuming such a simplified situation, the y and the z components just give 0 equals 0. So we don't have to bother writing those down. And our x component simplifies to this equation here. And what this is really expressing is this left-hand side piece is really du dt. That's how the x component of the partial velocity changes as following a parcel. And we're saying the changes in that velocity are going to be driven by this pressure gradient force, which I simplified just to this ratio of minus a over rho naught. So as the parcel moves, there's a negative tendency to its value. So it's going to tend to get more and more negative because of this negative sign term on the right-hand side. We're assuming a is greater than 0. So this particular example of a linear pressure gradient and a flow at rest turns out it has a very, very simple mathematical solution, because we can note, so we can now solve this. So let's now solve this equation. So let's now solve. So we have, just rewrite the same equation. So we can note the right-hand side of this equation doesn't depend on x in any way. Because we've assumed a linear pressure function, the gradient turned out to be a constant. And so our pressure gradient force on the right-hand side is just constant, doesn't depend on x. And so the two sides of this equation, they're equal. So that means if this side doesn't depend on x, then the left-hand side can't depend on x either. So this side does not depend on x. So left-hand side can't depend on x either. So let's look for solutions. Where u does not depend on x. That means we have u, which in general can depend on x and time. We're just going to say it just depends on time. So in that case, we have here partial by partial t plus u partial by partial x of u equals minus a over rho naught. But this d by dx is going to be 0 because u doesn't depend on x. So we can really change our partial derivative. Because our function only depends on one variable, our partial derivative changes into a regular derivative. And we get the very simple equation that the rate of change of u is just equal to this negative constant. And so we can integrate that from u equals 0 to u of t, to u dt, dt. Oh, sorry, this is not right. We can integrate from t equals 0 to t, du dt, dt equals the integral minus a over rho naught dt. And so we get here u of t minus u of 0 equals minus a over rho naught times t minus 0. So all I'm doing is we had this equation, just integrating both sides with respect to t. Because this is an integral, a time integral of a time derivative, we just evaluate that by just basically canceling out the integral of the derivative. So we get u of t minus u of 0. On the right-hand side, this is a constant inside the integrand, or the integrand is a constant rather. So we just get that constant multiplied by the difference between the endpoints, which is t minus 0. And so we assumed, based on our initial condition, was that the flow starts from rest. And so we get u of t is equal to minus a t over rho naught. So our flow is uniform, doesn't depend on x. It is strengthening in time. strengthening over time, and it starts at rest. So those three properties all make perfect sense with our pipe example, because we said it starts at rest. So when we put in t equals 0, we have to get 0 here, which we do. Putting in t equals 0, we get u equals 0. We'll also say it moves to the left, which is what we assume, which is what we thought from the beginning. We had a high pressure on the right-hand side of the pipe, low pressure on the left, and we expected to flow in the negative direction. And so our formula that we get out of the end makes sense. It's always negative. And then if we're applying a constant pressure rate, we're applying a constant force. So there's always a force acting, pushing and pushing and pushing. So because there's a constant force that never lets go, that means the flow gets faster and faster. Because there's nothing in our equations that resists that force. Later on, we're going to put in more ingredients, other terms in the equations that can provide forces that compensate. But for now, there's nothing to compensate for this pressure force, so the flow is just going to start going faster and faster down the pipe. So this example is, the mathematics is pretty simple, but it illustrates how, if we incorporate with our Euler equation, with our equation here, du dt equals minus 1 over rho times the pressure gradient. If we add to that something that constrains the density and something that constrains the pressure, then we can get a set of equations that we can actually solve. And in this case, we've set it to be so easy, so simple that the mathematics is really simple. But on future homeworks and so forth, you get examples that are still solvable, but somewhat more complicated. Okay. Now, of course, in general, we won't be able to make these very restrictive assumptions. We'll never be given the pressure unless we have observations. And we can't always make the assumption that the density is constant. And especially, we're going to talk about sound waves in a couple of classes. And sound waves, if you've ever studied those, say in a first year physics course, maybe second semester, sound waves are fundamentally compressional. So whether it's traveling through air or whether it's traveling through the water, each little parcel of water is like squeezing and expanding constantly. And that's how the pressure waves that are sound waves propagate through the air. So for a sound wave, you definitely cannot approximate the density as constant, because this squeezing and expanding is fundamental to how the waves work. So, okay, so this section is called closing the Euler equations in general. General solutions. So usually we cannot assume rho equals constant and pressure is not normally known in advance. To close the Euler equations, we need to invoke new physics. I'll say additional physics. And so to set the stage here a little bit, when we in the review part, I talked about how the Euler momentum equations really they come from F equals ma. They come from Newton's second law. So I can see some squinting. This says usually we cannot assume constant density and pressure is not known in advance. To close the Euler equations, we need to invoke additional physics. So recall that we derived Euler equation based on F equals ma, which is Newton's second law. So Newton's second law, we usually think about it as the force law. but also it expresses a conservation statement. So F equals ma is in some ways equivalent to conservation of momentum. So Newton's second law expresses the principle of conservation of momentum. I'll say in the absence of external forces. So for example, if F equals 0, if F equals 0, then we have 0 equals mass times acceleration. And acceleration is the derivative of speed. And if mass is constant, then we can write that as the derivative of mv, and that's equal to the derivative of p, where p equals mv equals momentum. And so if we have dp dt equals 0, that means momentum is constant, which in physics we often, instead of constant, we say conserved, meaning it doesn't change during the motion. And so if there's external forces acting on a particle, then it can inject or remove momentum. But a free particle that doesn't have any forces on it, it conserves its momentum. And so very often you'll hear people talk in fluid dynamics about the momentum equation. So rather than calling it the Euler equation, they'll call it the momentum equation. The Navier-Stokes equation, which we'll get to, is also sometimes called the momentum equation. And they call those equations that because they come from F equals ma, which fundamentally expresses conservation of linear momentum. Linear as opposed to angular momentum. So the point of this is that we use F equals ma, which is a conservation statement, conservation of momentum, and we use that to derive a dynamical fluid equation, the Euler momentum equation. So other physical principles can also be used to derive other complementary dynamical equations for fluids. So momentum conservation gave the Euler momentum equation. Other physical conservation principles give additional fluid equations. And so in physics, we talk about momentum conservation comes from Newton's second law. What are some other things that are often conserved in physics? Like, say, conservation of x. What would normally x be in random physics scenarios?
Energy.
Sorry?
Energy.
Yeah, conservation of energy is one of them. We're actually, that's not the first one we're going to do, but we're going to come back to that when we study sound waves. What else is generally conserved? Mass. Yeah. And so mass is what we're going to do right away. And of course, if you got into like relativistic fluids and conversion of mass and energy and stuff, and E equals mc squared, that's not for this class. That's high energy stuff. We're talking about non-relativistic fluids. So the speeds of the flow are small compared to the speed of light. So we don't have to worry about any of that stuff, and mass is conserved. So 2 examples are conservation of mass and conservation of energy. And each of these gives a dynamical fluid equation. So now we're going to start. This section is called conservation of mass, colon, the mass continuity equation. So now we're going to derive a new equation that's called the mass continuity equation, or sometimes just the continuity equation. And that's going to augment our Euler equation, and that'll be one of, remember we had 5 variables, 3 equations. So this will be a new equation, so then we'll only have one left to actually have a closed system. So what we're going to do here is consider mass flowing into and out of an imaginary box in the fluid. So we have a box here, and I'm not thinking of this as a fluid parcel. It's just an imaginary box. Just imagine you draw it like if you've taken electrostatics or whatever. It's kind of like a Gaussian surface, so you just draw imaginary boundaries. And we're going to track what's going into this box and what's coming out of it. So importantly, this is not a material parcel, and the box is stationary. And unchanging. Well, it's just stationary. So it's not moving with the flow. Okay, but I'm going to do the typical thing. I'm going to say we have an x coordinate here. We have a y coordinate into the page and a z coordinate up. And I'm going to put the center of my box at x naught. The right-hand side is x naught plus delta x over 2. The left-hand side is x naught minus delta x over 2. So we're just situating our coordinate system such that x naught is in the center of the box, is x naught, and then we have half of the whole width here is delta x, and so half of delta x to the right and half of delta x to the left. And then we're going to think about how much mass in the presence of a fluid flow is coming into and out of this imaginary box. We're going to sort of do some accounting, and then the simple idea is that that if more mass is going into the box than is coming out, then the mass of the box itself has to be increasing. And if more mass is leaving than is going in, then the mass of the box has to be decreasing, which is just a statement of conservation of mass. So if more mass enters the box than leaves, the mass of the box must increase. I realize now that I've probably gone over the limit where it's going to show up on the video. Okay, I'll try to practice in the future. Okay, so we're going to assume that we have some velocity field. There's going to be u of x, u of x, and some density field, rho of x. Okay. So, first of all, what's an estimate for the mass of the box? So what is the mass of the box? Well, our mass is equal to density times volume. In this case, is rho, and we're going to estimate that as being at the center of the box. So right at our center, we're going to estimate our density, and our volume here is delta x, delta y, delta z, assuming we have extents delta y in the y direction, and then delta z in the z direction. And the idea is that our box is going to be constant in time. So our box is not changing. And so if there is a situation where more mass is entering the box than is leaving, then if the mass of the box changes, then that has to be reflected by changes in the density. Because our delta x, delta y, delta z, these are all constant. But density may change to maintain mass conservation. So what we mean by that is if more mass comes in, rho is going to increase. If more mass leaves, rho is going to decrease. But this is just sort of the setup to think about it conceptually. So we're going to write down equations that say exactly how does the mass change, things like that. But this is the idea. So we're thinking about this box. There's fluid inside the box, but the density of that fluid is not necessarily constant. So you can think of it like a gas or whatever, like it can be compressed. And mass is going to enter in to this box on the various sides of the box. So for example, if you have a flow coming in on this side, flow coming in, then that flow can carry mass through this imaginary surface into the box. And likewise, if you have a flow on the other side, then mass can leave the box by that mechanism. So let's just, to start, let's just think about the flow in the x direction. So just little u. So how much mass is coming in at the left-hand side, and how much mass is leaving on the right-hand side? So when you have a fluid flow, that flow is going to carry mass proportional to how dense that fluid is. If you have a flow of a very dense fluid like lead, then the mass that carries is very high. And if you had a flow of a very low density fluid like a dilute gas, then it's transmitting only a little tiny bit of mass. So the mass flux, or mass transfer, is proportional to the speed of the flow u. So if the flow is going faster, it's transferring more mass, and the density. So it's a heavier fluid, it transfers more mass. So the mass that's coming in, and we'll find out that this is actually the rate of mass that's coming in, is equal to the product of these two factors. So it's equal to the velocity And we're looking at how much mass is coming in through this left surface. And so what we care about is the value of the speed and the density at the position of this left side. So the amount of mass that's coming into the box is going to be equal to u of x naught minus delta x over 2. So this is the speed at the left-hand side, multiplied by the density. The density at the left-hand side. And so this is the rate at which mass comes into the box. And now, very similarly, and we can check the units. So dimensions. Are the units of u times the units of rho, which is equal to the units of u times the units of rho, which is length per time, times, oh, I'm sorry, I left out one factor. This is why I checked the dimensions. So mass per length squared cubed. So one thing I left out here is the side walls also matter. Because if we're asking how much mass is carried into this box in terms of total mass, the bigger the box is, the more total mass there will be. So the amount of mass that gets transferred through this square that I've shaded on the left-hand side also depends on the area of the square. The bigger it is, if the flow is uniform over that whole square, the larger area you're looking at, the larger the amount of mass transfer. So we said the mass transfer is proportional to the flow, the density, and the area, which in this case is delta y, delta z. So I forgot to write in here delta y, delta z. And so now our dimensions need to be corrected. So the dimensions of rho u delta y delta z are equal to mass per length cubed times length per time times length times length. And so we see our three lengths all cancel out, and we just get mass per time. And so this expression that we've written down, velocity times density times the infinitesimal area of the, we're imagining this box is small, you can also think about a finite box. But for a small box with delta x, delta y, delta z dimensions, we find that this expression correctly gives us mass per time. This is the overall amount of mass that's coming into the box due to flow carrying that density into the inside of the box. Okay. So our mass out, the rate, is very similar, except now we need to look at the the right-hand side of the box, this shaded square. And so now we're also going to look at how fast, so your speed and your density and your area are all going to be the three factors that control how much mass is coming out. And so we can just write this down as u of x naught plus delta x over 2 times rho of x naught plus delta x over 2 times delta y delta z. Okay. So our rate of change of mass is now going to be the difference between these two rates. We have a rate of inflow and a rate of outflow, so the rate of change. If those two things are not equal, then you either have more mass coming in or you have more mass going out. And so the mass of the box is going to either increase or decrease. So the rate of change of mass in box is equal to mass in rate minus mass out rate. And that's going to equal, our mass in was u of x naught minus delta x over 2 times rho of x naught minus delta x over 2 times delta y delta z minus u of x naught plus delta x over 2 rho of x naught plus delta x over 2 times delta y delta z. And so much like we did with the, and there's a little derivative trick here. This is starting to look a little bit like a derivative because we have something evaluated at x plus delta x over 2 and something evaluated at x minus delta x over 2. So it sort of has the form of a derivative. But what I'm going to do is I'm going to pull out delta y, delta z, and delta x from this expression. So we're going to basically pull out the delta y, delta z, and then also multiply and divide by delta x. And so we get here the rate of change of mass in box equals delta x, delta y, delta z. Marker's kind of down here. Multiplied by and actually I'm going to pull out a minus sign also. And we're going to get here, so we'll pull out a minus sign, so that flips the sign of these two terms. So this term is going to become positive, that term becomes negative. And so this term here comes down here, and we get u of x naught plus delta x over 2, rho of x naught plus delta x over 2, minus this term comes over here, u of x naught minus delta x over 2, rho of x naught minus delta x over 2, and that all is divided by delta x. And now we really have something that's just a plain derivative, because if we think of the function, this is really equals minus delta x, delta y, delta z times d by dx of the function rho u. Because we take the function rho u and we evaluate it 1/2 a step to the right, minus 1/2 a step to the left, divided by our step. And that's in the limit that delta x goes to 0, that becomes, so this is a in the delta x goes to 0 limit. We have this expression. So our rate of change of mass in the box is equal to minus our volume element, delta x, delta y, delta z, multiplied by the partial derivative of the combination rho u. So this combination, density times velocity, that's our mass flux. And so the idea is that if this mass flux is changing, if there's a derivative across the box, that means it has to be higher on one side than the other, which means that the mass flux coming in and the mass flux coming out aren't equal, so the mass of the box has to be changing. So we had rate of change of mass equals minus delta v times d by dx of rho u. And this was only for the x direction. So if we had, I'll just pause for a minute. Is this too smushed? Would you like me to rewrite that? Is that okay? Or, it's okay?
That's good.
I'll just give a second to write it down. So this argument is basically saying that if the x derivative of the quantity rho u is not 0, then we have a net flux due to flow in the x direction, either into the box or out of the box, depending on if that derivative is positive or negative. But we only considered the x direction so far, but if we considered the y and the z also, just based on kind of matching the pattern, we can write down what it would be. So if we considered the y, which is v, and z, which is w, flow also, we would get two more terms, which would say rate of change of mass equals negative delta v times the term we already had, d by dx of rho u. And then the other two terms, I think you can probably believe, believe without derivation, are you just replace the x, we have an x derivative and the x component of the flow, so we change that to a y derivative and y component of the flow. So we get d by dy times rho v, and minus delta v times d by dz of rho w. And so this is the what's called this is the mass change due to flow in the x direction, mass change due to flow in the y direction, and mass change due to flow in the z direction. We can actually notice that this has a vector structure. We have x goes with x, y goes with y, z goes with z. So we can write this in a convenient form. As rate of change of mass equals minus our volume element delta v times the gradient operator dotted into the quantity rho times the velocity vector. And we can check that. We basically don't have time. Okay, so this thing here, del dot f for some function f, is called the divergence. So we talked before about the gradient, which is the gradient operator applied to a function, and this is the gradient operator dotted into a vector. And so next time we'll complete this derivation and show exactly how we can get an equation that tells us the density. So we'll do a quick reminder, and then we'll go from here. And then we'll also discuss what is this operator in general. So for people that are taking vector calculus, you may have already seen the divergence come up in that class, or not yet? Not yet? Okay. So it's coming up, it'll be coming up later. There's actually a cool theorem in vector calculus called the divergence theorem. We're not going to use the theorem, but we are going to use the divergence. And so next time I'll give an example of how to use this and how to interpret it and things like that. We'll leave it there for now, and we'll pick it back up again on Thursday. Yeah, we'll see if we have some. I think tomorrow is almost for sure. So we'll see.